Okay, so here's an example problem showing more detailed design for settlement problems where we have a soft clay site. As you can see here, a thick soft clay layers on top of consolidated fill layers, and also on top of like incompressible silty sand layer. So, and this site is proposed to build a high-tech industrial complex with a footing of 60 feet by 20 feet that sustained a loading of 200 tons. As you can imagine, we have a thick soft clay layer, and the settlements due to the 200 tons loading passing from the footings. Majority will come from the primary consolidations of the soft clay layer. And we are given the geotechnical informations. We know the thickness of each layers. We know the groundwater tables, which is in the interface of the field and soft clay layers. We know the unit weight of the 3 different materials, and also it is given lab results for the consolidation curve, which we will get into, that provide us the parameters we need for the design, such as the C sub C compression index, C sub R recompression index, and also the maximum pass pressure, often represented as the sigma pi P, and in your FE manual, it is represented by the P sub C. So P sub C, this value here represent as the FE manuals, which is the maximum pass pressure. And these questions have 4 parts, part A, B, C, and D, and which guide us through how to perform the settlements analysis for this problem, which we will get into pressure. So that's task A. So task number 1 here is from this lab results. We want to find the 3 parameters. First, the maximum pass pressure. And from this lab results, the Casagrande constructions have already performed it. And the details, you can go back to STM manuals or like my CE366 lecture at Cal State LA, the detailed Casagrande construction method. But here, in short, this is the point right there that can represent the maximum pass pressure. And if we go from there, we read from this log skills right there, which is this particular point. So this is my maximum pass pressure, P sub C. And again, like the textbook, we call that maximum, the sigma pi P or P sub P, but they mean the same thing, a maximum pass pressure. And we read from the log scales, this is 100 PSF from the x-axis, 2, 3, 4, 5, 6. So this is equals to 600 pound per square feet. So that is our maximum pass pressure. Next is we want to find our recompressions index, which is C sub R here. This is our C sub R right there, which is this slope. This is the slope that we want to find that represent the C sub R recompression index, or like this slope. Essentially, these 2 parts, they are parallel with each other. But the more ideal case when we have rebound recompressions slope after the maximum pass pressure. So as you can tell, like this portions of the curve is before the maximum pass pressure, and this portions of the curve afterward is after the maximum pass pressure. So the nice thing about the lower portion here is the soil samples in the lab have already experienced the maximum pass pressure. It has been low beyond this maximum pass pressure. So from a laboratory quality standpoint, the lower portion is more ideal for our data interpretations or for the C sub R characterizations, because this part of data, theoretically, it has been erased is a soil disturbance. So when we give it a chance that we can use the lower portions of the rebound part of the consolidation curve, we always prefer the later one, the rebound one after the maximum pass pressure. So we want to find out the slope of this line. So we will pick 2 points. First, we could pick this point here, and we read from the number we are reading about the x value here. We get about is 3,800. Again, reading from the log scales, we get about 3,800. We from there, this is what like roughly we got from the top, 3,800, and the corresponding y-axis we are reading about 0.6. So that's the coordinate pairs that we get, and we will get the other point here. If we are smart, we can pick something like easier to read. We can pick this point right here. So this point, we are getting the x coordinate to be 100, and the corresponding y is 0.81 of the y ratios. So just like a pond slope problems, if we got 2 ponds, then we can get the slope, and the slope is what we need, the C sub R. And remember in your FE manuals, the same thing here, it defined the C sub C or C sub R as here. So C sub R is right there. This equals to the delta Y divided by delta X, and in the consolidation curve, delta Y is the change of the raw ratios, and delta X is the change of the stress level. And it's a semi-log scale, so that's why you're seeing the log right there. But the FE manual just gives you the basic. Now you have a consolidation curve, then we need to interpret what we have. For this case, we want to find that our C sub R would be equals to the delta Y over delta X, because this is a slope. And the FE manuals, again, one more times, what is given is the delta E divided by delta log P. Delta E delta log P. So this is the P, the stress level. And in many textbooks, you will call sigma or sigma pi, in effective stress space. Is essentially they're the same thing. Meaning the stress level. So in this case, since we have a negative slope, and we understand that C sub R is a positive number, so we take off the polarity, we will multiply that by -1, and we pick this as a y2 and this as our y1. So we will do our math here, and over x2 minus x1, and this is a log scale. So we have this ratio, because just like go back to the algebra, the log x minus log y will be equals to log x over y. So here we have the corresponding values would be like a 3,800, and this would be a 100. So this is the case that this is our 3x00, and this is 100. It goes here and here. So it goes here and here, and the other 100 that we have is here, go to here. So it's just like pond slope calculations. And with that, we calculate the C sub R would be equals to 0.133. And very similarly, we also do a C sub C. And again, per the FE manual, this is the formula. And we, again, like it's like a log X minus log Y will be equals to log X over Y. So that's why, like, you know, it become a fractions when we deal with the minus or the difference between two lots values. And very similar here, we can pick this one too, and the other one we because we want to find the C sub C here, and we pick 2 points. We pick our point number 1 already. So at this point, we can recycle this point, and the other points that we can pick is we take advantage of E equal 1 here. So we can take this point, and we know the raw ratio is equals to 1. So easy to read on that one. And then we read our corresponding stress level. This time we are getting about 1600. So this one is this point here is about 1600. So this is 1,000. 1, 2, 3, 4, 5, 6 right there. So a little bit to my right. So there will be 1600 right there. So the other one, C sub C, again, we plug in the formula. Y2 minus Y1. So we have 0.6 minus 1, and also divided by log. This time is a ratio again. And it will be 3x00 divided by 1600. And we get our C sub C equals to 1.065. So those are the answer that we have, and pretty much the slope that we try to find there. And we need those 2 parameters for our latest settlements analysis. So pretty much we find out like the answer for part A, and we add on the solve properties to our solve profile. We know our sigma P point. We know the P sub C, the maximum path pressure, and we also figure out the C sub C and C sub R. And the second part of the questions asks you to find the distributed stress along to the center line of the footing. So we want to do pretty much a one layer, one sub-layer settlements analysis for just like a soft clay layer due to the structural loading applied from the footings. That will be pretty much part C. So we want to find the settlements due to add the soft clay layer here. And we are using like a one sub-layer approach. So we treat the whole soft clay layer as one layer. But before that, like a part B will ask you to find what is the stress, distributed stress at the midpoint. So if we want to treat it as a one sub-layer, the interested point for settlement analysis will be at the center of the footing and also at the middle of the layer, since we only have one layer. So the elevations we're getting is right at the midpoint. So this is 7.5 feet at the center of that clay layer, and also at the midpoint of the footing. So so first we want to find out the initial stress at the midpoint of the soft clay. Then we go ahead to do our stress analysis. First, we try to find the total stress would be equals to the field times the thickness here, 2.5 feet, and then plus the clay here, and then times the thickness at our interest locations, which is 7.5 feet. And we plug in the number, we will get the answer at 1013 pound per feet square. So this gamma field will be equals to 95 PCF, and the gamma clay will be equals to the 105. Okay, part B here is to ask to find the distributed stress along the center of footing at the midpoint of the clay layer. So we are particularly asked what is the distributed stress at this point, which is 7 and 5 feet below the interface of the field and the soft clay layer, at the midpoint of the soft clay layer, and also at the center point of the footing. So we want to know what is the distributed stress from the surcharge, which is the applied footing at the 200 tons structural load bypass to the soil through the foundations. And we know it is a discounted stress because the stress from the footing will be dissipated through the depth. So the amount of the loading filled by the soil will become less and less when the depth is increased. So right at the interface, we are feeling all the stress. But like at further down enough, maybe at like infinitive deep for sure, all the stress will be gone that provided by the footing. So it is feeling the stress right at this point is the 200 tons divided by the area. So right at the interface, or right at the grade level where the foundations is in contact with the soil layers at the ground surface or at the grade level. But at this point, at the midpoint right there, so the delta stress in your FE manual, it is represented by the delta P. So delta P is the induced change in consolidated stress at the center of the consolidated stratum. That's exactly what we're doing at the midpoint of the soft clay layer. And that will be equals to I times the surcharge. And Q sub S is the applied surface stress causing consolidations. And for this case, it is from the footing, the stress path passing from the foundations. So in this case, this is our surcharge, Q sub S. This is Q sub S. And at this elevations, at this like a depth right there, at this point, you will be equals to QS will be equals to the I factor times, just distribute the loading is the delta P equals to the I times QS. So in that case, I is the corrective factors or the inference factors. There are different like ways to find this I values. If you go back to my CE366 lecture, I have a lecture 6, if I'm correct. If the number is correct, is particularly talk about the stress distributions. And that's different method, like the 2-to-1 method to the DM 7.1, the Navy DM 7.1 method, and that's and also the Newmark method to find this I values. And the FE level, because of the time constraint and also the the length of the for the multiple choice problems, many times is restricted. So this I values very likely is all will be given. And this time, let's give you the I values is equals to 0.814. So we know the I values, and we can calculate the surcharge for the given 200 tons building loading. So the delta P, this case, will be equals to 0.814 times the 200 tons. And we know 1 tons is equals to 2,000 pounds divided by 1 tons here. So make sure all the units work out. And then divide by the area of our foundations, which is 60 feet times 20 feet. And we do our math here, and we will get the distributed loading is 271.2 on the square. So FE menu is delta P, and in some textbook you will find this many times represented by delta sigma, but they are the same thing. The delta P, the FE menu is many times equals to just a notations from different source. Some textbook you find it as the delta sigma. So that pretty much is part B. So part C now is asks you to find the settlements. The settlements form the foundation loading. And this particular questions asks you to use one sublayer approach. So to simplify our settlement analysis, we assume the distributed stress is uniform throughout throughout the whole layer. So that's why we pick the midpoint. We talk about that the stress, the induced stress from the foundations, the amount of stress will be dissipated with the increasing depth, which means like the loading, 200 tons loading should be greater at this point because it's closer to the footings. Should be greater than, much greater than at the top layers, could be much greater than at the bottom of the layers. But to simplify our settlement analysis, now we use the one sublayer approach. We assume that throughout the whole layer, the distributed stress are the same. So that's why we pick the midpoint. So kind of like an average, we take the midpoints to represent the distributed stress at the midpoint representing the whole layer. It's quick. This kind of analysis is quick, but as you can imagine, it's not so accurate because this is the fact that the stress is supposed to be dissipated with the increasing depth. Now we make a simplifications. We use the averagings. We use the midpoint to representing the whole layer and assume this the distributed stress is uniform. So, but anyways, this is our part C. We try to find the stress using the stress and then find the settlements. So this is part B answer right there, and part C. So the first thing we do is we find the total stress at the midpoint of the layer. That will be equals to the gamma field, which is 120 times the thickness, and then plus the new weight of the soft clay layer. And we are looking at the midpoint locations. So the thickness of of the soil layers we are dealing with now is half of the whole layers. So this is 7.5 feet. So this should give us the answer of 1,013 pound per feet square. And the pore water pressure equals to the unit weight of water times the water depth, is 7.5 feet again. So we got the pore water pressure, 468. And we can find out the effective stress equals to the total stress minus the pore pressure, which we should get at 544.5 pound per cubic square. So again, the notations in our FE manuals, this pretty much is our initial stress. Initial stress in our FE manual is P naught. So this is our initial stress, P naught. And we know our final stress because of the loading that we got from the foundations. We calculated this is the part B, what is the distributed stress at the point of interest. We always look at for settlements analysis, we always need to be very careful which point is your point of interest. For this time is the midpoint of the soft clay layer because we are doing one sublayer analysis. So we need to keep track with the stress and different scenario. So this is the initial stress at the midpoint before the foundations. So just the unit weight of the soils give us the initial stress, initial effective stress. And now we calculate the final stress. And the final stress is equals to our initial stress plus the distributed stress. So the initial stress we just calculate is 544.5. And the distributed stress we calculate is 271.2. So we add the two together, we get our final stress equals to 815.7 pound per feet square. So this is our final stress. And in settlements analysis, we always compare the initial stress and also final stress with one key stress number, right? And the stress number is from the soil memories. Remember, the soil always remember the maximum past pressure, which is this point. So that's why we need to conduct a consolidation test or odometer test to recover this information right here, this particular point, this very important particular point. What is the maximum past pressure that the soil has ever experienced throughout its history? And this case is 600 PSF from this consolidation test. And in settlements analysis, always good to recall this manual, this picture here. This picture is very important. So you always compare your initial stress and final stress with the maximum past pressure, P sub C. So in this case, we can construct our max consolidation curve. So this is our P sub C equals to 600 PSF, and our initial stress is 544. Actually, it's right here. It's less than the P sub C. And our final stress is greater than the P sub C, is 815. 0.7. And we also know the slope of the compressions part and also the slope of compression part. And settlements analysis pretty much is solving for the point slope problem of the consolidation curve with the known informations. And pretty much like, we want to find the delta E, right? Remember that? So this is the delta E. And this is the delta E2. So we want to find the delta Y, because we know the slope and the delta X. Delta X is the change in stress. So this is delta E2. So with those, if we find delta E1 and delta E2, then we can solve for the settlements. So in this case, next is we're going to use our equations to find our delta E1 and delta E2. So delta E1 is equals to C sub R times the recompression power, right? So pretty much like that, we can simplify it in this way. So the delta E is equals to delta E1 plus delta E2. And the delta E1 is equal to C sub R times the log P sub C divided by the P sub naught plus the C sub C, which is the other part right here, the delta E2 times log the P sub F divided by P sub C. So that is the delta E. And if we plug in the number C sub R, we find it previously this is 0.0133, and then the log P sub C we find out is 600 from the lab test results again, and P sub naught is 544, and the C sub C, given the case, is 1.065 times the log final stress 815.7, where P sub C 600, and we plug in all those numbers. The delta E we have is 0.148. And this equations shouldn't surprise us because it's also in the FE manuals. And we are at the scenario of the case that our initial stress is smaller than the consolidation stress, the maximum pass pressure, and also our final stress is greater than the maximum pass pressure P sub C. So pretty much like, this is my delta E right here. So this is my delta E right there, the change of the void ratios, and times this constant right there, then we get the delta H. So delta H is the settlements, equals to the delta E we find out divided by 1 plus E naught times the H naught. In this case, the E naught is not given, but we know the water content and also we know the specific gravity. So the same equations again. George Washington's is a soil engineer. So George Washington is a soil engineer, and at 100% saturations, so the initial water ratios will be equals to the specific gravity times the water content. So the specific gravity is 2.6, and the water content is given as 40%. So the E naught we have is 1.04. And the H naught is the thickness of the whole layer that we are calculating, and we are using one sublayer as our analysis. So the H naught is 15 feet, So delta E is given or is calculated previously is 1.48, 0.148, and the E naught we calculate is 1.04, and the thickness of the soil that we are dealing with now is 15 feet. And we do our calculations. Our settlement is 1.085 feet. That's our settlement. So that's our answer for part C. Okay, part D now, what we try to do is instead of one sublayer, we're going to perform analysis for two sublayers. So which means we're going to break down our soft clay layer into two equal thickness sublayers. So each have a 7.5 feet. So this is our first layer, this is our second layer. And we were going to repeat the settlements and analysis 2 times, each on sublayers, 1 time on each sublayers. And the particular locations, the depth we look at, again, is the midpoint. So we look at this locations and this locations. And again, settlement analysis is very important to know which exact locations you are considering. Is always the midpoint, but midpoint of which layers, and what like particular depth. So here will be particularly to be 3.75 feet down from the top for our first layer, and the second layers will be here. It'll be 11.25. feet down from the top of the soft clay layer. So for first thing we do is we look at the first layer settlement analysis. Again, what we do is first we calculate the stress first. So the vertical stress will be equals to the unit weight of the field times the thickness of the field plus the unit weight of the soft clay times again the locations that we talk about, which is 3.75 feet down from the top of the layer, and this gives us a stress of 656.25 pounds per feet square, and the pore pressure equals to 62.4 pounds per cubic feet times 3.75 pounds per feet again. That gives us a water pressure, a pore pressure, pore water pressure as 234 per feet square, and the effective stress equals to the P naught as indicated in the FE manual. That would be equals to the total stress minus the pore pressure. So this times we get 422. Next is we want to find the distributed stress at this particular locations. The distributed stress from the above ground surcharge from the footing, and the I value here, let's assume this is 0.842. So we can calculate our final stress final stress equals to the initial stress plus the I times the surcharge. And we know the initial stress we just calculate is 422, and the I value is 0.842, and the surcharge is 200 tons divided by the area times the inference factors again. So I'm repeating the calculation here because this part of calculations we have already complete in part C. So we can go back to see how the units work out, and this is like a PSF, and we need to do some conversions to make this become PSF again. This is just repeating some of the calculations in part C. So I directly put down the answer here. The final stress, we got 702. On 8 square. So we know the initial stress, we know the final stress. So this is my initial stress, this is my final stress. And we, in settlements analysis, we always compare that with the maximum pass pressure from the consolidation test, which is given, and we find it in part A. This is 600. And we know the initial stress is less than that, is 422. And our final stress is 703. So this is the final stress, and this is the initial stress. And when after we draw out the consolidation curve, it helps us to visualize which scenario we are at. So again, like if we go back to your FE manuals, we are at a scenario that our maximum pass pressure is sandwiching by the final stress and the initial stress, which is this equations here, just like a pass C. So we can put down the equations, which is the delta E will be equals to, or like, we can even put down the whole equations from the FE manual, and we are dealing with the first sub layer here, will be equals to the delta E, we know it already, we put down later, H naught divided by 1 plus E naught times the delta E. So the delta E have two parts, the C sub R times the maximum pass pressure divided by the initial stress plus the compression index times the log the final stress divided by the maximum pass pressure. So the key here now is H naught. H naught in part C, when we consider the entire soft clay layer as one layer, is equals to the thickness of the soil layer. And now what we're doing here, again, we divided the soil layers, the soft clay layer, into two parts, and we are doing with the first half only. So now the H naught that corresponding to the analysis we are doing here is half of the whole layer, because we are doing with the first, the one of the two sub layers. So here is, instead of 15 feet, this is 7.5 feet. So this is highly depends on how many sub layers you are. As you can imagine, if we are doing a 3 sub layers analysis, then this H naught will becomes like a 15 feet divided by 3. So far, so on. If you have 4 sub layers, then we divide by 4. So be very careful on how many sub layers you're dealing with. But we have already found that is 1.04. And the rest is just plug in the numbers. And some of the parameters we have already found in part A or part C. And C sub R is 0.133. C sub C we got is 1.05 times log. The final stress again for this problem is 703 and the maximum pass pressure. And again, this is just the first sublayer. And we put in all the number. We got the settlements of the first sublayer is 0.343 feet. Not the final answer yet, because it's just representing the the settlements due to primary consolidations from the structural loading due to from the foundations. For the first sublayer is 0.343 feet. We still need to find out the loading adding on the second layer. Okay, so this is the first sublayer, and then we deal with the second layer. And we do the same thing again. We need to find out the stress at the midpoint of the second layer locations. The same calculations. And now the location change. The depth we are doing now is 11.25 feet, because we are looking at this particular locations, which is looking at the midpoint of the second half. So we know this is half of the second half, so which is 3.75 feet. So plus the 7.5 feet, and we got 11.25 feet. So we got the total stress at that particular locations to be 0.369 pound per inch square. Pore pressure equals to the water unit weight. $702. And we can find out the effective stress, which is equals to the initial stress in our FE manual again. The total stress minus the water pressure. And we got the number of 667 pound per feet square. And in the second layers, let's assume the I factor on this locations is 0.693. Again, like, I'm giving you those I factor now, inference factors. In fact, there's a lot of different ways to come up with this I factors, the 2-to-1 method, the DM Navy 7.1 method. So, but for FE exams, likely this will be different because of the time constraint of the exam time. For more details, you can go back to my C366 lecture, the distributed stress lecture. But anyways, the next task, as like the previous first layer examples, so the final stress will be equals to the initial stress plus the I times delta Q, and the P naught now, this case is 667. And the I value is 0.693, and the delta Q's again is the 200 tons divided by the area of the footings. So again, this is just repeating calculations. The details unit conversions you can look at part C. We take care of the units, and this would be close to 897.6 per square. So once we get our initial stress and final stress in settlements analysis, it's always good to construct the consolidation curve. We know the pass pressure is 600 psf, and this time both our initial stress and final stress in fact is greater than the maximum pass pressure. So we are here 667, and also the final stress so for the case that both initial stress and final stress is greater than the maximum pass pressure, per the FE manuals, in fact, we only at the C sub C region, so we are in this case. So we can use that formula to find our settlements of the second layers. So this times the second layers settlements equals again this constants. This time we only have the C sub C. So same equations from the FE manuals. Plug in the numbers. The H naught, the thickness of the soil layer is not 15, right? Again, because we consider two sublayers. So this is the total thickness divided by 2. So this is 7.5 feet. Plus E naught, and E naught previously we have calculated that to be 1.04. And C sub C is the value we got from the consolidation test, 1.065 times log the final stress is 898, and the initial stress is 667. And we plug in all this number. The settlements for the second layers is 0.505 feet. So this is not the final answer, right? The final answer, the settlements for the two sublayers analysis would be equals to the settlements of the first layer plus the second layer. And the final answer is 0.849 feet, which is less than the one that we got from part C, which is roughly about 1 feet. But now here we got about 0.85 feet. So which one is more accurate? You can think of what actually we're doing here, right? We try to break down or use two different numbers. One is from the first sublayers, the other is from the second sublayers. And the number I'm talking about is the distributed stress. So instead of using one constant average distributed stress in part C, the middle of layers, this right here to represent the whole layer. Now we break it down into two sublayers. So we have one sublayer here to distribute the stress to represent the first sublayers, and later part, like the second sublayers, we updated the distributed stress. More like adjust to the fact that the stress is changing through the depth. So with more sublayers, the answer that we got is supposed to be more accurate. And you keep adding on sublayers to a point that you will see your settlements calculations results you get is no difference between n versus n plus 1 layers, or like the difference is within a tolerance that you set. Could be like a 0.1 feet or 0.2 feet, or like, even down to maybe 0.1 inch or 0.3 inch, depends on your design or how sensitive your structure is to the settlements. But at the end of the day, again, manually, I recommend you like, try maybe even like 3 sublayers, see what results you got. But like, if we do it in practice, we're likely like, all of these calculations can be programmed in computer computations. You can code it using like a MATLAB or other language, such that you can set the tolerance, and at the end of the day, you can see how the settlements affect by the different sublayers. But in practice, in learning hand calculations, it's always good to try a couple like a few sublayers. So that's all like on the examples I have here today is comprehensive settlements analysis programs. Please subscribe to my YouTube channels for more FE practice or Geotech questions practice example programs.